Okay, so now let's continue with life annuities with M3 payments. Okay, so consider a whole life annuity of 1 per year payable in installments of 1 over M at the beginning of each mth of a year while the person age X survives. Okay, so the payments are not made once a year, but it is done M times per year, and the size of the payment is 1 over M, and this is made at the beginning of each of those M's of the year. Okay, now let's define J to be the random variable representing the number of complete M's of a year lived in the year of death. And so, J is defined as the greatest integer value of the quantity T minus K times M. Okay? Remember that T is the time of death. We subtract K from it. So what is left here is the fractional part of the year. Right? This gives you the fraction of the year lived by the individual in the year of death. We multiply that by M and get its greatest integer value. So that gives us now the number of complete M's of a year lived in the year of death. Okay? So we note that there are M payments of 1 over M for each complete year lived, and therefore J plus 1 payments of 1 over M in the year of death. Right? So there are M payments of 1 over M for each complete year lived, and at the year of death, there would be J plus 1 payments of 1 over M. Okay? So, the value of Y, the present value of Y, the present value random variable Y using the aggregate payment technique would be equal to this summation. It's the sum of 1 over M times V raised to J over M, where J goes from 0 to M times K plus J. Right? There would be a payment of 1 over M paid at the beginning of each nth of the year. So the discount factor would be V raised to J over M, but J goes from 0, the first payment is made at time 0, up to the last payment that would be made after M plus K, M times K plus J periods. Right? Since there are K complete years and there are M payments every year, there will be a total of MK payments during the complete year, and during the fraction of the year, there would be J, J plus 1 payments. Remember that this starts at 0. Okay? And so, in terms of your theory of interest notations, that would be equal to the following. It's A angle K plus J plus 1 over M to the upper M. Remember the notation with the upper M in your theory of interest. And that is numerically equal to the following. That's 1 minus V to the K plus J plus 1 over M all over D to the upper M. So remember what D to the upper M is. If you recall your theory of interest, 1 plus I would be equal to the following in terms of D to the upper M, right? Where I is your effective rate of interest. Okay, and then another form of, okay, so when you get the expectation now of Y, right, this is what you get. This expectation of this V to the K plus 1 plus J plus 1 over M is actually capital A sub X to the upper M. So this is now the net single premium for this whole life insurance payable at the beginning of each end of the year, and then the payments are made. The payments is 1 over M at the beginning of each year. It's a whole life insurance. Okay? And then under the current payment technique, this is going to be our form. Okay? Now, let's talk about the relationship between these two actuarial present values. The one that is payable at the beginning of each year and the one that is payable at the beginning of each month of the year. The payments here is 1 per year. Here it is 1 over M. Okay? So we know the following from our discussion earlier, and from the previous slide, this could be obtained, right, from here. So you cross multiply and then you transpose that. That gives you the following identity. And this is from the identity earlier. This is 1 minus capital A sub x all over D is equal to A sub x double dots. And since these are both equal to 1, so we can equate this with the following. And that's what we did here. Okay, and then we just have to solve for this. So we transpose this and then divide by d to the upper m. We obtain the following expression. Right? We want to solve for a sub x to the upper m double dot. So we transpose that and then divide by d to the upper m. Okay? Applying UDD, we obtain the following from discussions before, and this is defined as S angle 1 to the upper m. These are notations that were lifted in theory of interest. And then this is true. It could be easily verified that this is true. Okay? And so if we plug in all of this here, so d over d to the upper m is equal to that. So we can replace this by this. So we obtain that. Okay? And then, yung a to the upper m, we can factor out ax first here. So this is 1. And this is going to be s sub 1 to the upper m. Right? So we obtain the following. And then we just have to combine these two fractions, the LCDs d to the upper m, to get that. And then we know that this ax from here is 1 minus d ax double dots. Right? And then just perform the operations and collect like terms. This is going to reduce to the following expression. Alright? And so we can rewrite this in the following way. We start off with this, and then we have the following. And then this is what we're going to do. We are going to define this as alpha of m, and this constant here is going to be beta of m. So that tells us the following relationship. So between these two actuarial present values is as follows. This is on the assumption of UDD, right? So a sub x to the upper m double dot is equal to alpha of m times a sub x double dot minus beta of m, where alpha of m is d all over d to the upper m times s angle 1 to the upper m. And since s angle 1 to the upper m is 1 plus I to the 1 minus 1 all over I to the upper m, remember? So d over d to the upper m times s angle 1 to the upper m. This is d over d to the upper m, 1 plus I to the 1 minus 1 over I to the upper m. From theory of interest, so this one cancels out. And so this becomes I times D times I to the upper M, D to the upper M. Where of course, I to the upper M is as follows, right? In relation to I and D to the upper M. And then beta of M is S angle 1 to the upper M minus 1 all over D to the upper M. And so again, this is 1 plus I to the 1 minus 1 all over I to the upper M times 1 over D to the upper M. Sorry. Meron pang dito. Teka. May minus 1 pa, no? Wait, this is wrong. This is 1 minus, no, 1 plus I to the 1 minus 1 all over I to the upper M minus 1 all over D to the upper M. Right? And so this cancels out. What we have here is I all over I to the upper M minus 1 all over D to the upper M. And so that gives us I minus I to the upper M all over I to the upper M D to the upper M. So this is beta of M. Okay? So in our life tables, usually what is given is this. So, but if you want the following, you just have to use the following identity. And again, this identity was obtained with the assumption of the UDD in the fractional age, in the year of death. Okay? However, a simpler relationship is the following. Okay? So we just subtract from this quantity m minus 1 over 2m. Okay? So to illustrate these assumptions, let's consider the following example. On the basis of the illustrative life table with interest at I equal to 0.06, calculate the actual present value of a whole life annuity due of 1,000 per month for a retiree age 65. Okay? So it's monthly payments of 1,000. So the yearly payment is 12,000. Right? So the yearly payment is 12,000. From our life table, this is the value that we obtain. We want now to find the actual present value for the monthly payment, wherein the M is equal to 12 and the monthly payment is 1,000, and it's a life annuity due. So with a simpler formula here, this is just going to be equal to the following, right? Ito lang yon. So that would be 12,000 times A angle 65 double dot minus 12 minus 1 all over 2 times 12. So minus 11 over 12. So this is the actual present value. Okay? If we use the UDD assumption, so this is going to be equal to the following. So we need to compute for alpha of 12 and beta of 12. So if I is 6%, so using this property, to get the formulas, we use this identity. I to the upper 12 would be 0.05841. D is 0.056603, and D to the upper 12 is 0.0581276. Okay, so computing alpha of 12, we know that it's equal to this, where M is 12. So that gives us 1.002810, and beta of 12, using the following, where M is 12, gives us 0.046811951. And so what we're looking for is this. So we just plug in those values where this is given to be the following. That gives us 113,179 as the actual present value. So there's a discrepancy, right, between the two quantities. Okay, I think I'll stop here now.